Essentially an apology. I would like to talk about a slightly different topic that I would typically present in the 3DOR community. I would like to be a slightly off topic, but I think the concepts, the notions that I would like to share with you are very relevant for the 3D vision community. So I hope you will bear with me and find this topic interesting. So basically, I would like to discuss an idea and some results of my own and my group's work on this, basically developing this idea in the domain of computational imaging. So basically, if we look at the way our hardware is built inside between our ears, so we have a pretty considerable amount of brain cortex volume dedicated to vision. Right? This is how we perceive world. This is how we describe world, and I think this is probably an even better, amazing depiction of how we perceive and describe world. So this cave drawing or painting is almost 40,000 years old, and basically because we really see the world in pictures, we have always also as human beings attempted to capture the visual description of the world, and this is one of the earliest imaging devices. This is camera obscura, and as any worthy thing that was known in Europe about the 1700, it was probably invented before by the Chinese and the Greek some 2000 years before. But again, it was widespread in Europe and was used in the 17th century, for example, to produce drawings and paintings. And some bed-tongues would even say that Vermeer was using camera obscura to produce his almost photorealistic paintings, and he actually used imaging devices for that. But of course, you need hours of painters' work to reproduce the image of the world. A real imaging device was invented with the invention of the photographic process that made the image persistent, basically automatically acquired without any human intervention. This is, I think, one of the earliest surviving photographs with the exposure time. Can you imagine 6 hours? And of course, from there, it was the beginning of a new era. So if we look at how this technology evolved in less than 200 years, so I think objectively, it's a huge gap. It's a huge way that was made from the first camera obscura until today's marvels of engineering and science that we see in our modern imaging devices like this one. But if you look under the hood, conceptually, they are not very different from the camera obscura. So it's the same, I would say, rather straightforward design. We have an optical system that collects the light from the scene. There is some photosensitive surface, which is digital, which is an electronic array of pixels, photosensitive elements that acquire the light and transform it into electric signals. And this is the image that we send eventually to the beholder. So this is how conventional cameras work. And in principle, this is no different from the camera obscura. However, we have, once the image has been converted to the digital domain, we have at our disposition today very powerful processors that can work on and process digital images. So we can put some amount of digital processing here, and instead of sending the picture directly to the beholder, process it digitally. And unlike the regular cameras that just show what the sensor sees, we can start talking about computational cameras where the image becomes intelligible after some amount of digital processing. So if we work on this path, so let's put a bigger amount of digital processing here, which is very affordable today, And let's be completely crazy with what we can do on the sensor and on the optics side. So the image might be unintelligible, but after some processing, some reconstruction process, we will get a nicely looking image. And of course, this idea is by far not new. So this is probably I don't know if you recognize this contraption, but it is actually the first CT scan, or at least the proof of concept of the first CT scanner. And this is the first CT image that was reconstructed using this device. The reconstruction time was more than 5 hours on computers back then, 50 years ago. But what is remarkable is that if you look at the raw readings of the sensors that receive the X-rays from the tube, you couldn't see this image. So the image is the result of some computational process from the raw data in which the image is at least not human intelligible. So this is, I think, this is the essence of computational imaging, that you need a digital process to reconstruct the image. So I think today we find ourselves in yet another interesting milestone that makes computational imaging even more exciting. So instead of the human beholder that eventually wants to see a nicely looking image, we have more and more machine vision algorithms that are the ultimate consumers of our images. We can imagine perception systems in an autonomous vehicle, for example. So there is no human in the loop. It will be unproductive or probably even harmful in such settings to have a human in the loop. So the only consumer of the image that an autonomous car perception system produces is a machine vision algorithm. So then, I think the natural question arises is, do we need an image at all? If we want to make some decision, for example, we want to brake the car in order not to run over a pedestrian, do we need an image, or at least a nicely looking image, for a human beholder to make this decision? So maybe we can do something else. So the concept that I would like to entertain ourselves with is, let's do what probably the nature did over millions of years of evolution. Let's try to think of all these imaging systems from the analog hardware, the optics, the electronics, and of course the digital part of the hardware. Let's just think of this as one single pipeline, endow it with learnable degrees of freedom, and learn it end to end. And so we will learn it end to end to optimize some specific task that the vision algorithm is entrusted with, and we can actually learn in concert this vision algorithm itself. So basically, we have a scene that we need to acquire from the physical world, and we need to perform some task on that scene. Let's learn how to perform this task from the acquisition itself until the decision that we are making, or until the parameters that we are estimating from the image, or whatever other task we might have. So basically, let's entertain ourselves with this idea. So what I'm going to show you next are different imaging systems and different computational imaging applications that I've been exploring together with my students over the course of the past few years. And I will show you some examples. Again, I will make it very non-technical. I apologize if you expect equation. Actually, I have not even a single equation in this talk, but of course I will be very happy to discuss details afterwards. So I will make it undetailed. So let me first focus on this device, the cell phone camera. So if you look at your cell phones, and we probably have more cameras, probably 2 or 3 times more cameras in this audience than the number of people. Basically, this device is nowadays how we communicate, right? Basically, we communicate with images nowadays. We use digital photography all the time to communicate. Since the invention of this device, it profoundly changed our way to communicate. But basically, there is a very strong driver in making the phone thinner and thinner, right? And you can see that the camera is the thickest part of the cell phone. And on the other hand, the number of pixels is continuously growing. So at some point you hit a physical limit, right? So the pixel needs to see a certain number of photons in order to produce a reliable signal. And this number is shrinking all the time. So one of the ways to counter this obvious physical limitation is to increase the hole through which the camera sees the scene, so we can collect more light. But if you do this, you hit a very obvious trade-off that is known to photographers under the name of depth of field. So if you take a conventional camera and you focus on an object, and you don't really do it manually as we used to do with the DSLR camera, for example, there is an automatic focusing mechanism in your cell phone. If we focus our camera on some object on some depth, objects that are too near will be blurred. So the camera will suffer from farsightedness. And the same way if we have an object that is too far from the focus distance. So basically, there is a range of depths in which the image will be sharp, and this interval is called the depth of field of the camera. And the bad news is that the bigger is the aperture compared to the focal distance of the camera, the more narrow is the depth of field. So on one hand, you get more light, but on the other hand, you get a very narrow depth of field. So what we try to do is to create, at least initially, that was my point of departure on this adventure into computational imaging, is to get kind of from both worlds. I want the light efficiency of a large aperture while keeping the depth of field of a small aperture. So basically what we did is we placed a special optical element that is completely transparent. It's just a piece of glass, but it has tiny bumps, microscopic bumps that manipulate the phase of the incoming wavefront. So essentially, just very roughly, what this device does, it focuses the different colors at different depths. So the way the mask, this phase mask, interacts with the wavefront depends on the wavelength. So essentially what you get on the sensors is this weirdly blurred image. Photographers call this chromatic aberration. It looks like these rainbow edges. Typically, even very cheap and decent optics try to remove chromatic aberrations as much as possible. And we introduce very precisely controlled chromatic aberration into the imaging system. So the image is, of course, of inferior quality. But what it gives you is that in a much bigger range of depths, some of the color channels is in focus, right? So you have sharpness in your image. You just need a computational process to recover it. This is what we do, and as a result, we get a sharp image. So again, going back to this concept of learning everything end to end, of course, you can learn a neural network, and this is how we did it in this work as well. You can learn a neural network to reconstruct a sharp image from this image that suffers from chromatic aberration. These masks can be very exquisitely simulated, so it is enough to train it on simulated data. However, the mask can also have different parameters. It can interact with the phase very differently. So we put those parameters as part of the learning process as well. And I will just show you quickly some results. So on the left, you see a regular imaging lens focused on the background. On the right, you see the same imaging lens with our new element added. And this is just a magnification. It has roughly MTF 2 times of the original camera. So it means that if you bring it into something like a cell phone camera, you might even not need an autofocusing mechanism at all. Again, it depends on the very specific parameters of the imaging system, but it makes autofocusing much easier, at least. And the light efficiency of the camera, of course, can be increased greatly. So you can continue taking selfies of yourself in a nightclub without having to noisy images. This is how it is the prototype. It looks like this is a phase mask on the left with these bumps that are, of course, hugely exaggerated over the vertical axis. They are just a few microns thick. But I think what is more interesting, so we started, so once we see that it works with enhanced depth of field, the appetite grows, of course, and we tried to solve some other problems. So one of the interesting things is that if you look